Hey guys, this is a review video for 7.5 through 7.6. For 7.4, I don't think I needed to do a review, but everything should be on there so you're a little bit more organized on what's going on in 7.4. But 7.5 is our last lesson of the year, which I didn't get a chance to go over, but it's all about linear regression and then taking statistics from linear regression and applying it to our parameter, which is our population. So in this example, it says a random sample of 11 high school were selected from Michigan. The percent of students who are free, reduced lunch, and the mean SAT math scores of each high school in the sample were recorded. Here are the data. So we have the high schools from Michigan, and then on the right side, we see their least square regression line as well as the data points that they have on here. And our goal is to figure out what type of association does our average SAT math score has with percent of free and reduced lunch. So here is one sample that we have and that we plotted, and there's also a line for it. What our least square regression line for this, what the difference is that we're going to take multiple samples. So we're not just going to take this set of 11 high schools. Maybe we take a different set of 11 high schools and then we plot those points on there. And then we're also going to plot another line. And then we're going to do that again and again and again. And ideally, the goal for us is to figure out what type of association does these two variables have with each other, whether is it going to be a positive association or if it's going to be a negative association. So overall, we're trying to find the absolute truth between these two. And in the real world, that is not ideal because there are like people multiplying every single day. And so to find the true relationship between those is pretty crazy. But our goal is to try to do that. And then the linear relationship, the line that I'm going to write for this one is y hat equals alpha plus beta times x. Alpha is going to be the true constant. Beta is going to be the true slope for the population. This line that we have right here is what we call the statistics, and we use y hat equals a plus bx. So this is a statistics. Right here is our parameter, okay? But to continue on, so here is the computer output for your least square regression line. So I've added in a few things that you guys should be aware of. But the norm is, this is our constant A, our slope B, and this right here is your estimated standard deviation, or you can call it your standard error. And this is the standard deviation that we're going to use eventually if we're either using confidence intervals or we're doing a significance test. Here's our test statistics. And then our p-values. So whenever we need to prove if there's evidence or not, we're going to use these values. Other things that you may possibly see is standard deviation of residuals, which is represented by S sub E. And we're not going to use this for this school year. And then our R square value, which explains the variation in all our points. And then if we were to square root that value, I get my R value of 0.923. Okay, so first off, that you see in here is the line of best fit, which again, I'm going to do y hat equals a plus bx. My A value here is, and then my B value. And then once I finish my line of best fit, I always have to label what my variables are. So here it is. Okay, so moving on to our linear regression T interval for slope. This will help us estimate what our slope is ranging in between. So the formula in terms of like doing intervals are going to be the same. So what we're estimating here is our slope. So we're going to use B plus or minus. We are going to use like our t-score as our critical value. And then our standard error is our S sub B. Sometimes you'll see it as SE sub B, which is standard error of my B. And then for the t value that I am, or the critical value that I'm going to use here is I'm going to use, I need to use the degree of freedom. And then I also need to use a confidence level. Since I don't have any here, I'm just going to make up a generic one. But the t critical value could be found in table B. And then when we look for degree of freedom, this one's going to be a little bit different. It's actually going to be n minus 2. So I'm going to do 11 minus 2, which gives me 9. And then lastly, I'm going to use a 95% confidence level. So again, generic. But let's say if I were to find that 95% confidence level, the value that it's going to give me is 2.31. But let me just plug in the rest of my numbers. So negative 1.993 plus or minus 2.31. And then I'm going to use my standard error. So I'm just taking that value from there. So what this gives me is this will give me, so at the moment, this is a statistics that we're using to estimate what the true parameter is. So this is ideally going to give me what my population might fall under. Okay, so that's how you do confidence level or confidence intervals. And then we're also going to do significance tests, which we also do with like each and every type of test that we have. But for linear regression t-test for slope, the main things that you guys technically need to know is what the test statistics looks like and how I calculate it. So it starts off with t equals, and then we have our slope minus our beta, divide that by our standard error of b. And then typically our beta here is going to always equal to 0. So we always want to claim that there is no relationship, and 0 represents that the slope is flat. So b is always 0. So like when I'm talking about my null hypothesis, you'll put beta equals to 0, and then beta is less than or greater than 0. So if I were to indicate beta equals 0 and I were to plug in the values, I would use these values. Okay, and that will give me negative 7.22. And notice that this is what our test statistics says, 7.22. So I know I'm doing something right. And the p-value, if I were to plug this into the calculator, I would get 0.000 out. So I will basically reject my null hypothesis. So there is a relationship. So some exam tips for this is just to use our b value to estimate our beta value, and this will be like the true slope when you write out the parameter. And then the conditions that you need to check is something called linear, or in a sense linear. So L represents that there's a linear relationship between x and y, and usually you can tell by the scatter plot, or you can tell by the residual plot. If it's random, there's no pattern, then you know your relationship is linear. If it's independence, you can use the n is less than 10% of capital N, which is the population. You can tell if it's normal. Sometimes you can assume this, and which is okay to assume at the moment because they're probably not going to have you check the conditions anyways. E represents equal variance, so they have the same standard deviation essentially, which is the same. And then just making sure your sample is random. And then lastly, if you want to take a look at a type of FRQ to practice, then you will use 2001's problem number 6. Okay, so that was 7.5, and then I'll move on to 7.6 in a second. So this is video 7.6 on type 1 and type 2 errors plus power. The example that we have today is Tacos El Conado claims that their giant burrito is half a pound on average, more precisely 8 ounces with a standard deviation of 1 ounce. Luke believes the average weight is less than that. He thinks it's 7 ounces. To test his claim, Luke goes to Taco El Conado and takes a random sample of 5 burritos. He will test his claim with an alpha level of 0.05. So the null hypothesis and the alternative hypothesis that I have here is that the Taco El Conado's giant burrito is actually half a pound on average. and then the alternative is less than that. So the type 1 error ideally is that I concluded that I rejected the null hypothesis, but in reality, that is true. So in terms of interpretation, I would write something along the lines of, we concluded that the giant burrito was less than 8 ounces, but in actuality, they were 8 ounces. So we may have caused them to lose customers, and that could have been my ramification for that, consequences for that. So let me just write that down. For our type 2 error, we have that we failed to reject our null hypothesis, but in reality, our null hypothesis is false. So what I would say here is that we concluded that the giant burritos were 8 ounces, but in reality, they were less than that. So as a consequence, we got scammed by Tacos El Cunado, and then we basically wasted our money. So moving forward is power of our test, and power of our test is when we make the correct decision. So the probability of us making the correct decision. To calculate that, we will do 1 minus the probability of a type 1 error, which is the same as the probability of rejecting our null hypothesis. To interpret my power, I basically need to know when I'm going to reject my null hypothesis. And this is actually all dependent on my p-value. Because my p-value is 0.5, noted from above, I need to basically figure out at what p-values will give me this idea of 0.05 and anything less than that. And this also depends on weight of my burrito. So at 7, is the weight of my burrito going to allow me to reject my null hypothesis or not? And I'm going to see at any value when this is going to work, so I know what is a good measurement to reject. So in order to take a look at this, I'm going to write out a statement, and then I will interpret each and every single piece of that statement so it makes a lot of sense. In this statement, what it says that I will reject a null anytime if I took my test statistics and I get less than or equal to 1.65. So my test statistics here is, this is my X bar value, which ideally is the weight that I get from my sample. So from before, I got a weight of 7. So I'm going to plug 7 in here and see if it meets this condition. I'm going to subtract it from what was claimed, and then I'm going to divide it by the standard deviation, which is the population standard deviation divided by the sample size of 5. So this 1.65 actually came from the z-score that I'm going to get when I have 0.05. So what I'm going to do is I'm going to look into my z-score table and see when I hit this 0.05 probability. So if I go in here to table A, I'm going to look inside the chart. And then when I look inside the chart, I can see that the closest I get is right around, maybe around here actually. So 1.65 is what I chose. Maybe you want to go 1.645. That's also okay, because we know that 0.05 is in between here. So that's how I got that value. And then just also ensuring that that value should be negative. Okay, so moving along is the idea of how do I increase more power? How do I enable myself to always make the correct decision? So one thing that I always want to do is always increase your sample size. That's an easy one. And then here, notice that I use context. So I'm going to increase it greater than 5 because my sample in this scenario is 5. And then secondly, I want to also increase my alpha value, which is 0.05. If I were to increase this value to, let's say, 0.10, then any value that I get that is less than 0.10, which will give me a better opportunity to reject. So that's why it's good to increase my alpha level as well. And then lastly, I have in the corner is just a table to help you with type 1 and type 2 error. So this is a different way to see it. But decisions are what I make in the middle, and then conclusions are what I did on the outside. So just relook at that and see if that makes sense to you. But that is the end of all of our reviews, and I hope that it had helped significantly and just filled in some gaps that you guys were missing. I wish you guys the best of luck on your AP exam, and definitely study a lot of the material before you take the exam, and don't forget to download the digital app as well. So you guys were wonderful. I will hopefully see you again in the future.